Hello everyone, hope everybody's doing well. Okay, so here we're going to talk about acid-base indicators briefly, and then we're going to learn about equilibria of slightly soluble ionic compounds. You guys have come across acid-base indicators before, and they are basically weak organic acids. You know, in an acid you can also have a conjugate base. So the beautiful thing in these weak organic acids are they have different colors in their conjugate acid and the conjugate base. Okay, so that's why it says here an acid base indicator is a weak organic acid. You can represent it as the protonated form of the indicator whose color differs from that of its conjugate base. Okay, it changes color going from acidic medium to the basic medium. So this ratio, concentration of the protonated indicator and the unprotonated indicator, is governed by the hydronium ion concentration of the solution. Indicators can therefore be used to monitor the pH change during an acid-base reaction. The color of an indicator changes over a specific narrow pH range, a range of about 2 pH units. So this diagram shows you some of the common indicators that we use in a lab and the pH range where they change the color, as well as the different colors that they give in different pH. So crystal violet, for example, at 0 degrees, 0 pH, it would be yellow, and then close to 2 would be blue. That's crystal violet, and thymol blue gives its color change in 2 different pH ranges. And then 2,4-dinitrophenol, bromophenol blue, bromocresol green, methyl red, alizarin, bromothymol blue, phenol red, phenolphthalein, alizarin yellow R. And I believe most of you have come across phenolphthalein. That gives you a color change, clear to pink. Going from clear to pink, clear would be in the acidic medium. As soon as it hits the basic medium, it becomes pink. That's what we had used in our general chemistry 1 when we were learning acid-base titrations. Okay. All right. So these are some of the acid-base indicators. And the color change of bromomethyl blue. So bromomethyl blue is this one over here. You see, at pH 6 it's about a yellow color, and then at pH 8 it is blue. So in between it kind of has a color between yellow and blue like this. Less than pH 6 it would be kind of yellowish. Greater than pH 7, 7.6, it would be blue, and then in between you have this color. So you have an idea what are the changes in the color of the indicators. Okay, so we use this to monitor the end point and the equivalence point of a titration. Okay. Now let's learn about equilibria of slightly soluble ionic compounds. Any insoluble ionic compound, meaning let's say you mix two reagents together and you show a precipitate form. And you will see that it precipitate out, it solidified out of the solution, and it is a solid. So these insoluble ionic compounds actually slightly soluble in aqueous solution. Even though they are precipitated out from the solution, they are slightly soluble in water. We assume that the very small amount of such a compound that dissolves will dissociate completely. So that little bit that they are going to soluble in water, they are going to make ions 100%. They're going to dissociate completely. For a slightly soluble ionic compound in water, equilibrium exists between solid solute and aqueous ions, like this. Let's say you have lead fluoride, which is a solid. This is slightly soluble in water, and when it is dissolved, it's going to give us the ions lead 2 plus and 2 fluoride ions. You see, because there are 2 fluorides, it should be 2F minus. So if you write the QC, equilibrium quotient, for this one, which we had talked about this in a previous chapter, QC would be lead 2 plus concentration and fluoride ion concentration raised to the stoichiometric ratio or the molar ratio of your fluoride, which is 2, and you divide it by lead fluoride concentration. Now lead fluoride here, it is a solid. Remember, we learned that the solid doesn't have a concentration, it's constant. So if you take the QC, equilibrium quotient, and the concentration of the solid together become another constant, we name it as QSP. S stand for soluble and P for solubility, and then the P stand for product. So QSP is a solubility product. Okay, so which is QC times lead fluoride, which is lead concentration times the fluoride concentration raised to the power 2, because there are 2 here. That's how you would write QSP, just using anything that represent as AQ, not the solid one. So QSP and KSP. QSP is called the ion product expression for a slightly soluble ionic compound. Okay, for any slightly soluble compound, let's say MPXP, which consists of ions M N plus and X minus, XZ minus, we can write QSP. This is the charge of the M and this is the charge of the X. M along with its charge, and then if this is your formula, how many atoms of P? How many atoms of M? Going to be P. How many atoms of X? Going to be Q. So M N plus raised to the power P, number of M ions, and number of X ions, X Z minus is the charge raised to the power Q. That's how you would write QSP, ion product expression. When the solution is saturated, then the system is at equilibrium. So then QSP will become KSP, the solubility product constant. SP stand for solubility product constant. Okay. The QSP value of a salt indicates how far the dissolution proceeds at equilibrium or saturation. Writing ion product expression. So we need to know how to write the ion product expression, and it's not that hard, it's quite easy. Write the ion product expression at equilibrium for each compound: magnesium carbonate, iron 2 hydroxide, calcium phosphate, and silver sulfide. The names are given. First we need to know how to write the formula. So magnesium carbonate, magnesium is plus 2 charge, carbonate is negative 2. So the formula would be magnesium carbonate, which is a solid. And then it will completely dissociate to give you slightly soluble, to give you completely dissociated ions. Magnesium 2 plus ion and carbonate negative 2. So when you write the KSP, you're going to write these 2 ions. It's 1-to-1 ratio. So magnesium 2 plus concentration and carbonate concentration. There are no superscripts or raised to the power since they are 1-to-1 ratio. And iron 2 hydroxide is, this is how you write iron 2 hydroxide. Iron 2 means iron has plus 2 charge, hydroxide is negative 1. So when you crisscross the charges, FeOH2. And they're going to dissociate into ions, Fe2 plus ion, and 2 hydroxides. And KSP would be these 2, iron 2 plus, and then hydroxide raised to the power 2, since there are 2 hydroxides. And calcium phosphate, this is how you would write the calcium phosphate. Trying to get the pen here. Okay, thank you. Calcium phosphate. Just to remind you how you would write the formula. So calcium is in group 2. So group 2 normally form charge 2 plus, and phosphate ion is negative 3. So when you put together the ions to find the formula, remember we did this, 2 goes here as a subscript next to the phosphate ion and 3 comes here. So that would make it calcium 3, phosphate 3. Sorry, phosphate 2. Phosphate 2. So that would have the charged balance compound, right? Since calcium is plus 2 times 3 of this will make it plus 6. Phosphate charge is negative 3 times 2 is negative 6. So by doing that, your positive charges and the negative charges are balanced and you have a neutral formula. Okay, that's how you write calcium phosphate solid. And then you dissociate into ions. So there are 3 calcium ions, so that will make it 3 calcium 2 plus 2 phosphate ions, 2 phosphate, and charge is minus 3. And then when you write the KSP for these two, you write calcium 2 plus, and then the charge, 2 plus is the charge and 3 is the molar ratio that would come here. And then the phosphate, PO43 minus, and your molar ratio or the coefficient will go like this. Okay. And silver sulfide, Ag2S, silver is plus 1, sulfide is negative 2 charge. So this is the formula that will give you 2 silver plus ions and S2 minus. So the KSP would be silver plus raised to the power 2 and sulfide ion. That's how you write the ion product expressions. Okay. And these are some of the solubility product constants of selected ionic compounds. They have different values. Okay. Okay, let's look at a problem here. Lead sulfate, we are given the formula PbSO4, is a key component in lead acid car batteries. Its solubility in water is given as 4.25 into 10 to the negative 3 grams per 100 milliliter solution. We want to find out the KSP of lead sulfate. And B is when lead 2 fluoride is shaken with pure water at 25 degrees Celsius. The solubility is found to be 0.64 grams per liter. Calculate the KSP of lead fluoride. How are we going to approach this? We're going to write the dissolution equation and the ion product expression for each compound. This tells us the number of moles of each ion formed. We use the molar mass to convert the solubility of the compound to molar solubility. So these are given in grams per milliliters. We need to convert them into molarity. Okay. Then use it to find the molarity of each ion, which we can substitute into the KSP expression. Let's first look at the first one, lead sulfate. 4.25 into 10 to the negative 3 grams per 100 milliliter solution. If you want to convert grams to moles, what do we need to do? We need to know the molar mass of lead sulfate. Excuse me. 1 mole of lead sulfate would be the molar mass of lead sulfate. And this is given for 100 milliliter solution, and we need to change it to 1000 milliliter solution. We have to find it to make it molarity. Let's see. Now this is our expression, lead sulfate, lead 2 plus and sulfate 2 minus. When you write the KSP, there would be lead 2 plus and sulfate ion. Converting solubility to molar solubility, you take the amount given in grams per milliliter, 100 milliliters, 4.25 into 10 to the negative 3 grams lead sulfate over 100 milliliter solution. And you convert it to liter. 1000 milliliters is 1 liter. Okay, and this will give us up to here converting it to liters. Now the next step is converting it to moles. So 1 mole lead sulfate is the molar mass of lead sulfate, which is 303.3 grams lead sulfate. Okay, so this will give us the molarity. You can see grams to grams get cancelled, milliliters to milliliters cancel. At the end you have moles per liter in units, which is the molarity units. So that give you 1.40 into 10 to the negative 4 molar lead sulfate. So first you convert grams per milliliters to moles per liters. Okay, and with that we can find out the KSP. Each mole of lead sulfate, remember each mole of lead sulfate give you 1 mole of lead ion and 1 mole of sulfate. So the lead ions and the sulfate ion also going to be the same amount, right? Because it's 1-to-1 ratio. So with that in mind, we can find out the KSP. That would be lead 2 plus times sulfate ion concentration, meaning you take both of these are the same amount raised to the power 2. That gives us the KSP. Okay, so that's what we did. What is the KSP of lead sulfate? So the part 2, when lead fluoride, now we have lead fluoride shaken with pure water at 25 degrees, the solubility 0.64 grams per liter. Calculate the KSP. Same way, just like we did earlier. Now it's given in grams per liter, so you convert this into molarity by using the molar mass of lead fluoride. Find out the molarity and write down first the expression for the ion product constant, lead ions and 2 fluoride ions, and then you plug the concentration terms and use the KSP expression to find out the KSP. So the dissociation of lead fluoride, lead 2 plus ions and fluoride ions, and when you write the KSP, that would be, we are missing something, it should be 2 fluoride ions, don't you think so? Because there are 2, PbF2, Pb2 plus 2F minus, that should be a typo. So when you write the KSP, that would be lead 2 plus and fluoride ion raised to the power 2. We were given 0.64 grams lead fluoride per liter. Converting it to moles by using the molar mass of lead fluoride gave us the concentration for lead fluoride as this. And then we need to find out what are the concentration of lead and fluoride according to this equation. 1 mole of lead fluoride gives you 1 mole of lead. 1 mole of lead fluoride gives you 2 moles of fluoride. So we have to use that ratio. Lead 2 plus would be the same amount. So the fluoride would be 2 times of this. 5.2 into 10 to the negative 3. And then when you put it into the KSP expression, lead 2 plus 2.6 into 10 to the negative 3. And then the fluoride is going to be this amount. And then raised to the power 2. That will give us the KSP. Okay. Good. Okay. So earlier we were given the solubility and we found KSP. Now this example shows us if you are given KSP, how can we find out the solubility? Calcium hydroxide is a major component of mortar, plaster and cement. And solutions of calcium hydroxide are used in industry as a strong and expensive base. We want to calculate the molar solubility of calcium hydroxide in water if the KSP is given. Now we're going to do back calculation. KSP given. Again, the first thing is we're going to go ahead and write down the equation, expression. Okay. So calcium hydroxide, calcium ions is going to dissociate into calcium ions and 2 hydroxide ions. And we were given KSP. When you write the expression, KSP would be calcium 2 plus hydroxide 2. And the number is 6.5 into 10 to the negative 6. So we can put this in terms of a initial change and equilibrium ratio. We know the value of KSP. So we set up a reaction table that expresses calcium and hydroxide. Sorry about that. Calcium and hydroxide in terms of S, solubility, the molar solubility. We then substitute these expressions into the KSP expression and solve for S. Okay. Let me quiet this. I can't do it yet. I will quiet it. Okay, so let's see. Calcium hydroxide, we have initially solid. Initial amount, nothing is being formed. So we can just say it is 0. Okay. And then the change. Let's say the amount of calcium and hydroxide being generated by dissociating calcium hydroxide is S. This is 1, so it is plus S, and since there are 2 hydroxide, that would be 2S. So at the equilibrium, we don't have to worry about this one because it's a solid. What you have at the equilibrium is the amount that has been produced, S and 2S. Okay, because there's nothing to begin with, so it's going to be the same amount. So the KSP, which is the same expression we wrote, calcium ions to hydroxide. Now we put them in terms of S. S for calcium, 2S for hydroxide. And still we need to raise it to the power 2. So when you do this calculation, S, 2S raised to the power 2. So 2S times 2S is 4S2 times S, 4S3. So KSP is 6.5 into 10 to the negative 6. So then S would be, you take this amount and you divide it by 4. That will give you, let me show you, S3 would be 6.5 into 10 to the negative 6 over 4. And when you try to find out the S, so then the S would be then cube root of this, what you're going to get from this calculation. Okay. First you will do calculation here under the cube root, and then you take the cube of that. That will give you the solubility. Okay. That's how you would calculate solubility if the KSP is given. Relationship between KSP and solubility. So you can see that the higher the KSP value, the greater the solubility, as long as we compare compounds that have the same total number of ions in their formulas. When you have a higher KSP value, solubility is also higher. As long as we compare compounds that have the same total number of ions in their formula. So the number of ions in magnesium carbonate, 2, cation to anion ratio is 1 to 1. So KSP 3.5 into 10 to the negative 8. And their solubility 1.9 into 10 to the negative 4. 2 ions again here, 1.6 into 10 to the negative 8. 1.3 into 10 to the negative 4. So as the KSP increases, the solubility increases. See? Barium chromate, 10 to the negative 10, 1.4 into 10 to the negative 5. And with these are when you have 3 ions, number of ions. Cation to anion ratio is the same. 6.5 into 10 to the negative 6, 1.2 into 10 to the negative 2. So higher KSP and higher solubility. Okay. Just a comparison. Excuse me. The effect of a common ion on solubility. So this here you have a lead chromate, which is slightly soluble salt, forms a saturated solution. Lead chromate, and it is in equilibrium with the lead ions and chromate ions. So let's say you add sodium chromate solution. What happened when you add sodium chromate? Do you think the solubility will increase or solubility will decrease? According to the Le Chatelier's principle, when you add in sodium chromate, you are adding chromate ion which is to the right side. When you add one of the products, what's going to happen to the equilibrium? It will reverse the reaction, right? Because we want to come back to the equilibrium. Now that you have more of the product, equilibrium will shift, making more of lead chromate, right? So then what happened? You are making more of the lead chromate, so the solubility will decrease. The amount of lead chromate will increase. So by adding a common ion, you can see how the solubility decreases as well as the reactant amount increase. Effect of pH on solubility. Changes in pH affects the solubility of many slightly soluble ionic compounds. So when we are looking at the solubility, meaning the solid that we have formed, is what is going to happen to the solid depending on the pH. Okay, so the changes in pH affect the solubility of many slightly soluble ionic compounds. The addition of hydronium ion will increase the solubility of a salt that contains the anion of a weak acid. Now let's see, you have calcium carbonate. It's a solid. So it dissociates into calcium ions and carbonate ion. And the carbonate ion is an anion of a weak acid, hydrogen carbonate. How is it going to increase the solubility? Let's look at that. So once you form carbonate, now we are looking at what happened to this calcium carbonate when you add acid. So you generate carbonate due to this dissociation. And this carbonate ion can react with the added acid, forming hydrogen carbonate and water. So if it forms hydrogen carbonate and water, so the next step would be hydrogen carbonate with additional hydronium ions can grab another proton and form carbonic acid, H2CO3, and water. H2CO3 is a very unstable acid, carbonic acid. It decomposes to give you carbon dioxide and water. So eventually what happened? The carbonate is going to used up. So you are losing carbonate ion. You're going to lose carbonate ions. If you lose carbonate ions, what happened to the equilibrium? It will shift to the right. So as a result, what happened to the solubility of the calcium carbonate? Increases, right? So the net effect of adding hydronium ion or an acid to calcium carbonate is the removal of carbonate ions, which causes equilibrium shift to the right. More calcium carbonate will dissolve. So in the previous slide, we saw by adding a common ion chromate, decrease the solubility of the solid. Now in this case, adding an acid which has an ion of a weak acid will increase the solubility according to this formation of carbonate reacting with hydronium to give you hydrogen carbonate, then to the carbonic acid, and then forming carbon dioxide and water. Predicting the effect on solubility of adding strong acid. Write a balanced equation to explain whether addition of hydronium ions from a strong acid affects the solubility of each ionic compound. We have lead to bromide, copper to hydroxide, and iron to sulfide. Okay. First we have to write the balanced equation. And then we're going to see if any of these ions are going to react with hydronium ion added. We write the balanced dissolution equation for each compound and then note the anion. The anion of a weak acid react with hydronium, causing an increase in solubility. So lead bromide. We have lead 2 plus and bromide ion. Now bromide ion is an anion of hydrobromic acid, hydrogen bromide, which is a strong acid. So it does not react with hydronium ion. The addition of strong acid has no effect on its solubility. Okay, it has to be an anion of a weak acid, but bromide come from the strong acid HBr. And then what about copper 2 hydroxide? Copper 2 hydroxide, this is the formula. It's going to give you copper 2 plus and 2 hydroxide ions. And hydroxide is the anion of water, a very weak acid, and is in fact a strong base. It will react with hydronium ion. Hydroxide is a strong base, but it is the anion of a weak acid, water. So this hydroxide is going to react with hydronium ion by giving water. So if hydroxide react with added hydronium ion, what's going to happen to the solubility of copper hydroxide? Increases solubility. And then lead sulfide, Fe2 plus S2 minus is what it's going to form. Okay, here it's going to give you Fe2 plus and S2 minus. Now sulfide is the anion of Hs minus, which is again a weak acid. Remember the strong acids, 6 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. So Hs minus is a weak acid and is a strong base. Strong base is sulfide anion is a strong base, but Hs minus is a weak acid. So it will react completely with water to form Hs minus and hydroxide. Both ions will react with added hydronium ion. So the Hs minus, sulfide will react with hydronium ion to give Hs minus, will react with hydronium ion forming H2S and water, and as a result it will increase the solubility. Okay. Predicting the formation of a precipitate. For a saturated solution of a slightly soluble ionic salt, QSP equals KSP if it is saturated. When two solutions containing the ions of slightly soluble salts are mixed, if QSP equals KSP, the solution is saturated and no change will occur. If QSP is greater than KSP, a precipitate will form until the remaining solution is saturated. If QSP is less than KSP, no precipitate will form because the solution is unsaturated. Okay. Let's see by using that concept whether a precipitate will form. A common lab method for preparing precipitate is to mix solutions containing the component ions. Does a precipitate form when 0.1 liter of 0.3 molar calcium nitrate mixed with 0.2 liters of 0.06 molar sodium fluoride? We are given the volume and the molarity of calcium nitrate, and we are given the volume and molarity of sodium fluoride. First, we need to decide which slightly soluble salt could form by adding these two together. So calcium nitrate and sodium fluoride, when you mix together, what are we going to form? So these are the ions present: calcium ions, nitrate ions coming from here, and then the sodium ions and fluoride ions. And all sodium salts and nitrate salts are soluble. So the only possible precipitate is calcium fluoride. And its KSP value is 3.2 into 10 to the negative 11. When we mix these two together with the given amounts, if it exceeds the KSP value, then we will see a precipitate. If it is less than this value, then we will not see a precipitate. Okay, so the precipitate is calcium fluoride, and it will dissociate to give you calcium ions and fluoride, and then the KSP expression for this would be calcium ions 2 plus and then the fluoride raised to the power 2. Now let's use these given values to calculate the molarities. We need to calculate calcium ions and fluoride in the final solution. Number of moles of calcium ions, 0.03 molar calcium solution, and we were given 0.1 liter solution. So this is the molarity times the volume will give us a number of moles. So the number of moles of calcium ions 0.03. Now this many number of moles are in the combined volume, which is 0.1 liter and 0.2 liter, 0.3 liter. So you have to divide it by the new volume that we're going to get after you mix the two solutions. So 0.03 over 0.3 will make it 0.1. Okay, molar calcium solution. And then the amount of fluoride, molarity of the fluoride solution 0.06, volume 0.2. So 0.012 moles fluoride. Okay. So the number of moles of fluoride is 0.012. So the initial number of moles of fluoride would be that number of moles over the volume. The total volume, added volume 0.1 plus 0.2, 0.3. So when you get this calculation done, it would be 0.04. Okay. So the QSP, first we're going to find out the calcium ions 0.1, fluoride 0.04 raised to the power 2. 1.6 into 10 to the negative 4. So this value, which is the QSP 1.6 into 10 to the negative 4, is greater than KSP, which is this 10 to the negative 11. So calcium fluoride will precipitate until QSP equals 3.2 into 10 to the negative 11. Okay. So the selective precipitation is used to separate a solution containing a mixture of ions. A precipitating ion is added to the solution until the QSP of the more soluble compound is almost equal to its KSP. The less soluble compound will precipitate in as large a quantity as possible, leaving behind the ion of the more soluble compound. Okay, that's what we do if you want to do a selective precipitation. A precipitating ion is added to the solution until the QSP of the more soluble compound is almost equal to its KSP. Okay, so that concludes our session for chapter 19.